After the definition of moments, we can define variance. And essentially what variance is a measure of the distance between the outcomes and the mean. So remember our example earlier. So it's 0, 1, 2, 3, 4, 5. Let's say you have an outcome at 1 with the probability of 1 over 4, an outcome at 4 with probability 1 over 4, an outcome at 2 with probability 1/2. Okay, so the mean is here, 2.25. This is the mean. And for each outcome, let's say I have a sequence, and the first outcome is 1, then 4, and then another 4, and then 2, another 4, 2, 1, 2, etc. So what you want to do is compute the average distance between each of the outcomes and the expected value. So this is the distance for this outcome, and this is the distance for this outcome, this is the distance for this outcome, etc. But you see, if you actually subtract the mean from each outcome, the average will be 0, because this distance will be negative, this distance will be positive, and on the average they will cancel each other out. And you can take the absolute value, but it's difficult to work with absolute values when you have further derivations, because it's not an analytical function. So what you do is you take the square of each of these distances and take the average of the squares. Okay, so the function you compute is x minus the mean value squared and take its expectation. So k minus the mean, by the way, this is an alternative notation for expected value. And take the distance between the possible outcome and the expected value, take the square, weight with the probability, and add them up. This is what we call variance, and it is a measure of how dispersed and how widely spread the distribution is. If the variance is large, we understand that the possible outcomes are distant to each other. Or if the variance is small, then we understand that the possible outcomes are closer to each other and they are tightly packed. Small variance means small or relatively smaller randomness, and large variance means a larger amount of variation. Now, expectation, as I mentioned, is a linear operator. Therefore, if you expand this expression, the definition of variance, take this square, expand it, x squared minus 2m times x plus m squared. Now, m here, the expectation, is a constant number, okay? And when you, there are 3 terms here, so separate them because expectation is linear. This is the second moment, and you see this is the mean, and this is the expected value of a constant, which is a constant by itself. So this is m squared. So this is the second moment minus 2 times the square of the mean plus square of the mean. So what you get is the second moment minus square of the mean. And this is another relationship we frequently use to compute the variance of a random variable. Another issue here is, by the definition of variance, you see, the order of the variance is defined in terms of x squared. For instance, if your random quantity is, let's say, the height of people in a classroom, let's say. So in our classroom, let's say we have, 20 people, and I measure the heights of every student in the class, make a note of it, and then I obtain the expected value, which is again in terms of, let's say, meters. Okay, so 1.83, 1.68, 1.72, 1.58, 1.90, etc., etc. I have a data. Okay, I take their average. What I get is the expected value, well, the sample mean in this case. But if you have the random variable, modeling this data, you have the expected value. And since it's a weighted average, its order is still meters. However, if you compute the variance, since you are working with the square of this quantity, it's going to be in terms of meters square. Okay, so you do not want this. We would like to have this measure in the same order as x. Therefore, we take the square root. And what we obtain is called the standard deviation, which is again in the same order with the random quantity. And by definition, neither variance nor the standard deviation can be negative. Both of them are non-negative, greater than or equal to 0, because in the definition, you've got a square there.